In both SN1 substitution and E1 elimination reactions of alkyl halides, the rate-determining step is loss of the leaving group, the first step that forms the key carbocation intermediate. So when we think about solvent effects and structural effects on the rates of SN1 and E1 reactions, it's all about this initially formed carbocation intermediate. And in fact, the effects on rate for SN1 reactions are the same as the effects on rate of E1 reactions, since the step controlling the rate in both cases is the same, the formation of this carbocation intermediate that's common to both mechanisms. We'll discuss the E1 reaction in more detail in a separate video. In this video, we're going to focus on rate effects on SN1 and E1 reactions, keeping in mind throughout that these relate entirely to this common initial first step in both mechanisms, the slow formation of this carbocation intermediate. When it comes to solvent effects, I think the first thing worth noting is that a polar solvent for an SN1 or E1 reaction is absolutely necessary. Since ions are formed in the slow step of the reaction, stabilization of those ions is critical for the reaction to proceed at an appreciable rate. So a nonpolar solvent like hexane or benzene is going to be terrible for SN1 and E1 reactions. But within the category of polar solvents, we have these two types, protic and aprotic solvents. In the SN2 reaction, protic solvents are actually disadvantageous, actually slow the reaction by hydrogen bonding to the nucleophile. For SN1 and E1 reactions, however, polar protic solvents accelerate the reaction dramatically because hydrogen bonding stabilizes the ionic products of the initial loss of a leaving group step. And so we have a different solvent effect here where polar protic solvents are advantageous for SN1 and E1 reactions. It's all about that first step in which the carbocation and the conjugate base of the leaving group, for example, Br- or Cl-, are formed. This table shows the effect of various solvents on the rate of this ionization step, which is common to both the SN1 and E1 mechanisms. Going down the table, from water at the top to diethyl ether at the bottom, the dielectric constant of the solvent is decreasing. This is a measure of the ability of the solvent to stabilize ions. And it's decreasing from water to diethyl ether. Water is fantastic at stabilizing ions, and diethyl ether is not great. It's very weakly polar, and it doesn't have hydrogen bonding donors. It doesn't have OH or NH bonds. Notice also that the rate is decreasing as we move down this table for this ionization step. So we've got 40 for the relative rate of water. Ethanol is kind of our standard rate of 1, and we've got 10 to the negative 5 is the relative rate of diethyl ether. So we've got 6 orders of magnitude between these two solvents in terms of the rate, and so we can see the kinetic advantage provided by polar protic solvents is dramatic in this reaction. Use of alcohol solvents and water is quite common. The structure of the alkyl halide also plays an important role in the rate of SN1 and E1 reactions because loss of the halide anion produces a carbocation, and the substitution pattern and structure and stability of that carbocation depends on the substitution pattern and structure of the initial alkyl halide. And so we can think about this really along two dimensions that are important to consider: the substitution pattern of the alkyl halide and the possibility of resonance stabilization in the carbocation. More substituted carbocations are more stable than less substituted carbocations. Therefore, more substituted alkyl halides, which can lose the halide to form a more substituted carbocation, react more rapidly in SN1 and E1 reactions than less substituted alkyl halides. When it comes to the nature of the leaving group, the better the leaving group, the faster the reaction. So alkyl fluorides are basically unreactive in SN1 reactions. Alkyl iodides are most reactive because iodine is the best leaving group in this series. It's the most stable with negative charge, especially in these protic solvents due to its polarizability. The possibility of resonance stabilization in the carbocation is also important to consider. Allylic and benzylic halides react pretty rapidly in SN1 reactions, and this can be surprising because these can look like primary, and in fact be primary, alkyl halides. For example, benzyl bromide, which is a primary alkyl halide, nonetheless reacts quickly in SN1 reactions. And this is because loss of the bromide leaving group produces a resonance-stabilized carbocation, right? And we can see that benzylic carbocation up above, and it's actually a good opportunity to pause the video and draw resonance structures if you need to make sure you can see that this cation is resonance stabilized. Same goes for allylic halides. Allyl bromide, allyl chloride. These can lose a halide anion to produce a resonance-stabilized allyl cation, and so those alkyl halides react relatively rapidly in S and 1 and E1 reactions.